From the grand, sweeping spiral of a galaxy to the silent, invisible orbits of an electron, the universe is always dancing. It's a dance of curves, a waltz of orbits, this constant turning that shapes pretty much everything we see. So today, we're going to learn the steps to this fundamental rhythm of physics, circular motion.
Just look around your world for a second. We tend to build with straight lines, sure, but nature's default setting is the curve. The universe itself, from the tiniest atom to the biggest galaxy, moves in circles. And this isn't just random movement, it's a performance, a beautiful dance that's governed by some really precise rules.
So, to understand this cosmic dance, we've got to start with the basic steps. What exactly is this constant turn we keep talking about?
To put it simply, circular motion is just the movement of an object along a circle. All you need are two key ingredients, a fixed point right there in the center, and a distance from that center that never ever changes, which of course we all know as the radius, or r.
Okay, now this is where things get really cool. An object in a perfect circle might be moving at a constant speed, let's say 10 meters per second, right? But its velocity is constantly changing. So why is that? It's because velocity includes direction, and on a circle, your direction is changing every single instant. Honestly, getting this one distinction is the key that unlocks everything else we're about to cover.
So, to properly describe this dance, we need a specific language, and that language is called kinematics. It's basically how we take familiar ideas like distance and speed and adapt them for a world that's all about curves. Instead of measuring how far something travels in a straight line, we measure how far it has rotated. We call this its angular displacement, and we use the Greek letter theta. Now, you'll probably notice we measure this in radians. Don't let that trip you up. Just think of it like using meters instead of feet. It's a unit for angles that just makes all the physics equations work out a lot more nicely.
So if angular displacement is how far it's turned, then angular velocity, represented by omega, is how fast it's turning. It's the rotational version of speed, telling us the rhythm of that turn in radians per second.
But what about the actual speed you'd see on a speedometer? Well, that's called the tangential velocity. It's the speed of the object along the edge of the circle at any given moment. And this is where it all clicks together. This velocity, v, is simply the radius r multiplied by the angular velocity omega. This is exactly why on a merry-go-round, the person on the outside edge feels like they're going way faster. They have a larger radius. And understanding this velocity, the one you actually feel, is the key to unlocking the forces that choreograph this whole performance.
So this brings us to the big question, why does an object turn? I mean, according to Newton's first law, an object in motion wants to stay in motion, in a straight line. So if it's turning, something must be constantly pulling it away from that straight path. So what's the unseen partner that's leading this dance?
That pull is an acceleration. We call it centripetal acceleration. Centripetal literally means center-seeking. This acceleration isn't changing how fast the object is going. Its one and only job is to constantly change the object's direction, yanking it inward to keep it on that circular path.
And here's how we calculate it. The centripetal acceleration equals the velocity squared divided by the radius. So, what does this actually mean? It means the faster you go, the more acceleration is needed to keep you turning. It also means the tighter the curve, a smaller r, the greater the acceleration required to make that turn.
Now, wherever there's acceleration, Newton's second law tells us there must be a force, F equals ma. So by plugging in our formula for centripetal acceleration, we get the master equation for the force needed to keep something moving in a circle. The centripetal force equals the object's mass times its velocity squared, all divided by the radius. This is it. This is the choreography of force written in the language of mathematics. So, and this is a really crucial point, centripetal force isn't some new magical force. It's more like a job description. It's the net inward force that is provided by something real and tangible. For a planet, that force is gravity. For a ball you're swinging on a string, it's tension. For a car turning a corner, it's all about the friction. All right, enough with the theory. Let's take these principles out onto the dance floor of the real world and see how this inward pull shapes everything from our solar system right down to our highways. For a satellite or a planet, gravity is the tireless dance partner that provides the centripetal force. The Earth's gravity is constantly pulling the moon inward, which prevents it from just flying off in a straight line into deep space. It's a perfect, delicate balance between the moon's forward momentum and Earth's inward pull. When a car goes around a turn, it's the static friction between the tires and the asphalt that acts as the centripetal force, pushing the car toward the center of the curve. This is why if you go too fast or hit an icy patch, that friction isn't strong enough and the car's inertia just takes over, sending it skidding off tangent to the curve.
We see this in sports, too. In the hammer throw, the athlete has to provide an absolutely massive centripetal force through the tension in the chain. As they spin faster and faster, that velocity increases like crazy, requiring an incredible amount of tension to keep that heavy ball from flying away before the moment of release.
So as we kind of zoom back out, you can start to see that this isn't just a collection of equations. It's a story. It's the story of how a few basic principles can combine to create one of the most common and, frankly, most beautiful forms of motion in the whole universe.
At its very heart, circular motion is the result of a battle. You have inertia, which wants an object to go straight. Then you have a centripetal force pulling it inward. And the result of this constant tug-of-war is the elegant, perfect geometry of a circle. It's a powerful reminder that even the most complex movements are governed by simple, profound rules. So the next time you see a car round a corner, or look up at a planet in the night sky, or even just swing a set of keys on a lanyard, remember the invisible dance that's happening. Remember that constant inward pull, fighting against the desire to fly straight. It makes you wonder, doesn't it? What other invisible rules are out there, orchestrating all the beautiful, complex motion all around you?